Let's do another example of substitution as a technique for integration. And in particular today, what I would like to show you is an example of a definite integral using substitution, as opposed to the indefinite integrals that we were doing in the last video. Now, looking at this expression, can you see an instance of a function and the derivative of that function? I think the one that stands out to me is that we have sine of x appearing in this expression, and right next to it we have cosine of x, which is the derivative of sine. So if I think of sine of x as equaling u, and I think of cosine of x as equaling du dx, then I can think of du as cosine of x times dx. Now, I have the option to solve for dx, get 1 over cosine x du, but as you do more and more of these problems, you will begin to try and find some shortcut, some ways of streamlining your thinking and your process to reduce the time that these problems require. And one of the techniques that you will see used quite often is that they will only partially solve for dx. Here I've written this as a du equals cosine x dx. And then I will go back in to the integral and replace the instance of cosine x dx with du. This can be quite nice sometimes. If you see a big quantity like this as you're solving for du, and exactly the same big quantity shows up in your integrand, you can replace those usually quite quickly. So now I will go in and I will replace sine x with u, and I will replace the cosine x dx entirely with the du, which I know that that expression is equal to. But at the moment, there is something fundamentally incorrect about the integral that I have written, and that has to do with the limits of integration. You see, originally, the limits of integration that I was given in this problem are limits that are given in terms of x values, start at x equals 0 and finish at x equals pi. And at the moment, these two numbers are still x values. When we're doing substitution, our goal is to rewrite everything in terms of x, so that it's in terms of u instead. And in the case of a definite integral, that process must be done not only for the dx portion, not only for the integrand itself, but you have to replace the x limits with u limits. Replace the x limits here with u limits. Okay, so that brings us back to the statement that u represented sine of x. If I want to know what u is doing when x equals 0, I can simply plug x equals 0 into this equation to find that u is 0 at the exact same time. When x is pi, u is equal to sine of pi. So, fascinatingly, this u value is 0 on both the left and the right hand side of this region. So now, what are we actually integrating? We're integrating from u equals 0 to u equals 0 of u du. But because both the left and the right hand limits are identical, we are integrating under this function u over a region which has no width at all. So the net area under this function will be 0 because it's just not wide enough to have any area. The left and the right hand limits are exactly the same. And so 0 is the result of this calculation.